Thank you, Lindsay. Can you hear me okay? Yeah, good. I'll talk a bit louder if needs be. Thank you very much. I've got lots of demonstrations to show you, and I'll have to stop halfway through to get the next box open, so we'll have a little break about 25 minutes in. The title of my talk, Putting the S into Mechanics. The S does not stand for Seffen. Let's just be clear about that. It stands for my subject, which is structures. And a structure is any object which is loaded or sits within a loaded environment. And the theory of structures is structural mechanics, which you may know is related to the more familiar topic of statics. And one reason for giving this talk is that prestige, because it's one of the oldest analytical subjects, does not entitle it to a kind of sort of modern day relevance without asserting that particular relevance, particularly as we sit in an age where the digital side of engineering seems to be advancing almost relentlessly. So I have like-minded colleagues in the sort of physical engineering sciences say we need to keep putting the M into mechanics to keep our subject relevant. And I think there's a really important S to enunciate there in the form of the sort of structural mechanical side of engineering mechanics, and beyond what you typically think of its application within structural engineering, which is to build stuff out of concrete and steel. But any object that is loaded must have structural integrity, and I would argue that aircraft, the challenge there is perhaps greater because it sits in the ground, it flies, the loads are both dynamic and static, the mass of the aircraft is changing, and all the while it has to be relatively lightweight. And when you consider that for the Airbus A380, the weight of the jet engines alone is equivalent to 12 family cars, 4 elephants, it's quite impressive that this thing flies at all. Well, it's not impressive, it's aerodynamics, but anyway, it sort of works and works very well. Even terrestrial structures that are built with a sort of material economy in mind, because material and labor is time and money, and so thus over the centuries, 2 forms of sort of architectural layout, structural form, if you like, have emerged that make use of material economy. And on the left, we have the sort of discrete layouts that you see, and these are sort of slender bars, beams, and rods connected at discrete joints to create these sort of triangulated forms. But equally efficient on the right, beg your pardon, we have this sort of continuous dome roof of the Santa Maria Cathedral in Florence. So it's a surface, if you like, and if you take a few roof tiles off and poke through that surface, you'll find it's quite thin. So it is very efficient, and it operates like a sort of shell from nature. And engineers build structures that are safe by following these codified, these sort of regulations, if you like, of good practice. Now, for those in the audience that perhaps aren't familiar with terms, engineering structures are made of elastic materials, so they stretch and compress under loading. And the resistance to that loading is met by the stiffness of the structure, a bit like a spring, and the stiffer the structure, the less it deflects, and so on. And I should say that deflection, displacement, shape change, movement, distortion, these are all synonymous terms, if you like. So the 3 criteria that engineers work to is that the stiffness, whilst bearing material economy in mind, should be such that the largest changes in shape are less than 0.3% of the size of the structure. The strength of the material from which it is made is not compromised, and everything that it does is predictable. It doesn't go unstable. It's giving us a response that is certain. And you can summarize that sort of connection between the structural and material in this simple linear equation where on the right side we have an indication of the maximum strain of the material, which is around 0.2, 0.3% anyway itself for the typical engineering materials that we sort of work with. And by strain, we're talking about the relative changes of length within the material. So in this bar that you see in the bottom left there, when you pull it such that it extends by an amount delta, then that divided by the length structurally is directly equivalent to the material strain that you see. But on the right there, the beam that's bending through a central point load deflects by an amount delta in the middle, but that divided by the span gives you a strain that's also delta over L, but indirectly through the assumption that the length to depth ratio, this L over B term, is greater than 10. But nevertheless, engineers sometimes get this wrong, particularly when you have a sort of new architecture in play, and the Millennium Bridge opened in June 2000, and all rather publicly it had on show this sort of flaw in its design where the lateral, the side-to-side stiffness was too small. It would wobble from left to right, and many thought this was a publicity stunt to garner media attention on the day. But really that wobble fed into the mindset of the people walking across the bridge. It literally synchronized their steps, and they all began to compensate together. And 2,000 Londoners moving from side to side generates a pretty large sort of sideways force, which increased the wobble, which fed back into their mindset, and then this problem began to grow out of control. And you'll see whole swathes of people here starting to move together in what is known as autoparametric excitation. This problem was known in early long-span suspension bridges, which would suffer from the phenomenon of galloping, and the most famous of which is the Tacoma Narrows Bridge here in Washington State, which on a windy day in early December 1940, you can see here began to gallop, and that gallop ran away, and shortly after this video was filmed, it indeed collapsed. But you can see here that the movements are certainly of the order of several percentage points, if not 10% of the length of that particular span. So again, we have this kind of exceptionality of loading event, and Igor, who produced this simulation, a former member of the group, shows what happens if you don't dampen or mitigate those wobbles. All bridges will wobble, if you like. It's how you get rid of that. And this is a cross-section through the bridge, and there's a flow coming from left to right. And the bridge is wobbling, we're not getting rid of it, and you'll see it generates this oscillation in the flow behind it. These vortices kind of spool off the bridge, pull the bridge down, they kind of kick against it, and the bridge springs back. But this introduces at the front, where the air is hitting it, this greater sort of disturbance. You'll see the orange flow, if you like, then beginning to feed into the vortices at the back, making them bigger, making the kick larger, and then suddenly this begins to run away, and it's sort of end of days for the bridge shortly after that. So structures change shape. They move. We build them to be relatively lightweight. We accept that they move. We try to contain that movement. But I've made a career in research terms out of making structures deliberately change shape, what we call shape-changing structures. I've got to be careful here about expressing loyalties because my civil engineering boss is in the audience, but my first love is really aerospace structures, the structural mechanics, if you like, of aircraft, spacecraft, satellites, that sort of thing. So I used to go to conferences where the great and the good would stand up saying, you know, if we're going to build these aircraft of tomorrow, we have to have structural mechanics that allows the shape of the wing to mimic what you see a bird doing in biology, where the wing will change shape to adapt to the aerodynamic flow. So it can sprint, for example, quickly to a scene of interest, or it comes into land on a much sort of shorter runway than expected. So it changes the planned form of the wing, so it can maximize what it can extract from the sort of the aerodynamic loads in this, so it can do what it does effectively, like a bird coming into roost here on a perch, if you like. But I'll remind you that if we even allow sort of engineering materials to have a little bit more strain, you're not getting close to the limits of ostensible shape change that will allow that. But if you look around you, there are examples of shape-changing structures there. This is mostly a flexible solar sail, but at the center of it, there's a little motor and a guidance system. You'll see it deploying itself. It sort of opens out, it explodes open, if you like. And that enables it to be folded with many others, so you can launch them into space at the same time. And then they gather themselves into a little swarm and sort of spin around the Earth once they've deployed beaming solar energy back to the Earth. And this is a project that's led by Sergio Pellegrino at Caltech. He was formerly here in Cambridge and my PhD supervisor. And in the sort of mid to late 90s, during my PhD, I worked on a sort of primitive form of this self-deploying technology. You'll see what becomes a radio dish in this slow motion footage emerge from the fabric being pulled out by white metallic strips, and these strips are coiled around the central hub, and they store elastic potential energy, and that gets converted to kinetic energy as it gets drawn out here, as you can see. So this takes about 1.5 seconds in reality from start to finish. Sony, in sort of marketing the flexibility of their plastic LED display some years ago, were keen to show that it was so flexible you could roll it around this motorized tube. That's really important because it enforces a protective sort of limit on the degree of how far you can fold it, because if you don't have that in place and you fold about a line, you get this horrible damaged crease running along the center of your flip phone, as you can see. But if you look around you, there's technology in the home that can be deployable. Deployable because you want to store it in a folded, compact way, but you have to open it, and in opening it, you latch it, you lock it to give it some kind of structural integrity. So I'm entering the last phase of my academic career, and I thought, well, perhaps I have enough experience and wisdom to put this stuff all down on paper in terms of writing a textbook. And it's a book literally of two halves of geometry and mechanics of the possibilities of shape change versus what you need by way of the structural mechanics to make that happen. And I'm going to talk about some of these principles now with a little bit of demonstration. I think it's important that we do write textbooks. We've lost, if you like, that sort of ritual and custom, I think, because of the way in which research has become commercialized. Maybe I'm platforming here slightly. But I think it's incumbent upon us to educate the next generation. And to do that, you should be writing textbooks. And I'm sort of aiming that message at any sort of mid-career academics in the audience. So let's talk about compliance. Now, compliance literally means you've got something which is already flexible. What can you do by way of shaping that? In this case, I'm going to talk about surfaces and the shaping of surfaces via generators. And the trusty engineer's piece of cardboard clearly tells you, you've got a flexible surface here. And what I mean by that is that if you have a surface which can be curved, you can either curve it about a cylinder or curve it about something which tapers like a cone to create these surfaces upon which you can draw straight lines. And those straight lines run at right angles to the direction of curving. And because you can draw these straight lines, you've got what's called simple curvature or simply curved surfaces. And James Clerk Maxwell suggested the projection of those lines onto the plane of a page in order to generate an impression of the surface, which is why these are called generators, these lines. Eric Mansfield, working at the Royal Aircraft Establishment for 30-odd years, took it a step further and said that out of the infinitely many generators that you can draw on the surface of the thin wing of a fast jet, that only one of them will exactly satisfy the work balance of the aerodynamic forces that are causing that curving out of plane to the energy stored within the bent wing, and what he calls an extensional theory. Inextensional because the material is curving, it's not stretching. But an effect that is perhaps felt up and down the country most weekends with regard to the flexibility of surfaces is what I call the pizza effect. And the pizza is like a thin surface that sort of droops, and you can draw some straight line generators on this. But we all know that with pizza, if you curve the base, you can straighten the pizza. So then you can eat the pizza with a little bit more sort of dignity. And here's a little bit, sort of a demo with something a little bit more sort of handleable in terms of size. So the generators, I should say there, are orienting themselves at right angles to this radius of curving that you see there. So that was the demo. We did a project with an undergraduate, ACOS medic. We tried to understand the relationship between the triangularity of the slice and the radius of curving at the base. No matter what you did, you always got the end of the pizza drooping a little bit when you do this properly. So you can sort of see this here when I sort of kick this out and let it go a little bit. You see the front drooping a little bit, but this is a property in proper experiments. Now the reason for that is if you assume that your pizza is simply curved, then every cross-section moving towards the tip is a circular arc of diminishing width and depth. That depth is there as the moment of inertia to create structural depth, which helps you to carry the leveraged weight ahead of that cross-section, which generates this reactive torque, which we call a bending moment, M. It too diminishes as well. So there's a lot to take in there. But the point is, if you plot those variations normalized between the base at 0 and 1, the tip, you see that the eye sort of goes off at a faster rate and almost disappears 2/3 of the way along. If you plot the ratio of M to I, which is to say what is it that you need to carry relative to what's available by way of structural depth to do that, then you'll see it kind of blows up again towards the end 2/3 of the way along, which is kind of what we're seeing. And so if your structure is not able to furnish that demand, you'll see it sort of dip at the front there. Okay, so that's compliance. I'm going to talk about mechanism here with the tagline, articulating catastrophe. So these are kind of scissoring units where you have bars, so pairs of bars connected in the middle and connected to each other so that when you articulate, they kind of go in this sort of linear motion, and we're kind of familiar with this. This allows you to change the position between, say, a mirror and a a receiver on a satellite or to reach inaccessible heights using these scissor lifts. Sergio Pellegrino, again at Caltech, recognized, and this is the catastrophe part, is that these structures you see aren't structures, they have no stiffness, they're quite floppy. But if you were to weave cables through the structure, you can arrange for those cables to become exactly straight as you've deployed it. So the tension in the cable acts to provide stiffness, if you like, by proxy. If you move the position of the central pin so it's no longer central, like we have here, and you articulate it, then it goes in a kind of curved path, as you can see, and a more tightly sort of arranged curved path. And that's quite useful, but what's a better arrangement is to use a sort of scissoring pair connected in the middle, but where there's a kink. And the kink creates an outside sort of, it creates a divergence, if you like, between the outside pins. And rather unusually, that remains fixed, that angle, irrespective of the articulation angle. So you get these little sort of units sliding up and down these kind of triangular channels. And if that channel is exactly one whole fraction of 360, you can connect them to form a ring. And so you produce something which is a little bit more useful. If I sort of switch to the screen, can I just switch to the overhead here? I didn't see it on screen there. So just to that. So what I've got here, perfect. So what I've got here is, so this is a pair of units with a sort of kink here in the middle, and to prove the point that this kind of operates as a ring, you can see it sort of opening and closing like so, and clearly it works quite well. And this, more usefully appointed in something like this, we need to go back to here. So again, you can create slightly more sophisticated versions of these. This gives you the template for the moving parts that might then become the movable parts of a stadium roof that opens and closes in sort of bad weather. I'm going to digress slightly and talk about this arts and crafts pursuit, which is entitled slice forms. And this is where you create sort of volumetric shapes by taking slices through the original volume at right angles to each other. This creates slices with a profile on the outside. And with the complementary slots, you can sort of reform them to produce a sort of discrete version of the original sort of volume. This is why they're called slice forms. And you don't have to have slices that are vertical or at right angles to each other. And in this rendition of a torus, where the slices are passing through the center, it generates a profile in the slices that is circular, what's known as a Valarso circle for the French geometer that discovered it. So I have one here, and you can see it's quite a sort of lightweight structure. It's got a lot of air, it's made of card, and it's quite sort of stiff. So we were interested in their sort of structural mechanics, their load-bearing capability. So you have to have a scheme for how you make these. And that involves taking a slice, a reference slice, rotating it in two directions, in this case a rectangular plane. You produce two complementary sets of slices, and then you bring them into intersection and say in some kind of drawing software to identify where the radial slots have to go. The endpoints are, if you like, in the colored dots here. And then you submit that to a laser cutter, you cut the slices precisely, and then you build it and you end up with the structure. However, you don't build it all at once because you have to assemble the slices in sequence. And we discovered that this, in fact, was deployable. It could move. It was mechanistic. And what you see in the video is what I have in my hand here. It's this sort of almost three-dimensional volumetric version of a pantograph, with scissoring planes with hinge lines. What's beautiful is that they fold into this flat stack. They can be opened so far as the sort of design configuration that you work with. And this one is deliberately helical, so the ends don't sort of ever meet, but it locks out. You can't move it past this sort of final lockout position without some jamming taking place in the structure. And so we were interested in this as a kind of form of sort of mechanistic motion. And so with Tim Watson, a PhD student, we decided to look at that. And so what you do is you think about what each plane is doing within the slice form. So you can imagine if this is behaving as a mechanism, then what starts off as a green plane should remain a red plane as you open and close this. But this is an over-constrained mechanism because the slices kind of talk to each other. They're slotted at different intervals. And the relationship between the angle of that slice theta relative to the opening angle beta. It depends on where the radial slot is, this kind of eta term that you're seeing over here. So theta, as you move along the slice, and the white dots are different sort of slot positions, will vary. And when you plot that variation against the opening angle, you find that in the flat folded configuration and the open configuration, they're exactly the same, but they gently deviate in between, which is to say that as you're opening these, as I was just doing, the slices, as you open them, the slices individually are gently rotating within themselves. They're kind of flexing and curving ever so slightly. And when you get past the sort of design configuration, when you get to this lockout phase, you can see the angles kind of ramp up exponentially. It begins to jam, which sort of explains what's going on. Not to diss software. You can use software to do interesting things like create slivers instead of slices, and you can arrange for these kind of birdcage-like sort of forms, and indeed a sort of an asymmetrical rendition, an artist's interpretation of the Beijing Stadium there, if you like. But that's the end of that, and so now we're going to move on to folding, and this is forming vertices out of plane. This is all about repurposing origami principles for producing engineering materials of the type that you sort of see here. We've got this sort of origami sheet that can be compressed and sort of pulled apart, and it's quite lovely. But I'm not going to talk about that because I don't have time. I don't have time to talk about elastofolding, which is the kind of curved version of this where you have what happens to a surface if you fold about a curve. But I'm going to finish that off as a nice segue to the next section by showing you this example, which is a sheet of paper with some fold lines in this that are inclined to one side. And if you fold about those, you create a sort of spiral shape that you can see here. And that spiral shape, however, if you force the ends together to make this a simply curved surface, then if you look carefully at this, and this is badly shot, by the way, you see that the lines, the fold lines, are no longer lines, they're now curved. But look at the paper in between. The paper in between them takes on this sort of rather different form. And if you do proper experiments and take proper photographs, you'll see that going along the axes of this sort of configuration, the paper strips are curving downwards in that direction, but they're also curving around. There's two components of curvature here. So this has double curvature. It's no longer simply curved. And that brings us nicely onto the sort of final geometric principle, which is to do with Gauss, the German genius, and double curving. Now, we all know that this triangle is wrong, not because the side lengths of pi r over 2, but rather the internal angle should not be 90. They should be 60. We all know that. Hold that thought. Here's a sphere with some circles drawn on the surface. These are great circles because they have the same center point as the sphere. We have an equatorial or an equator circle. And then we have two polar circles on the right, separated from each other by 90 degrees. That allows us to identify 3 points in the circle where pairs of points are common to pairs of circles. And if we then go on a journey, if we walk from the North Pole to the equator and get to that point at the red, and then proceed to the yellow, we have to turn through 90 degrees, and we get to the yellow to get back to the North Pole, we have to turn through 90 degrees as well. So we create a three-sided object on a sphere, a spherical triangle, where clearly the internal angles in this case are 90 degrees. And so if you take a flat surface, a flat triangle here, and the side lengths being pi over 2 are coincidental because it can exactly fit onto the surface along its edges, but everywhere else, with respect to what's happening in the corners, you will see the corners have to expand from 60 to 90 degrees. The material has to stretch, and that stretching is a consequence of the fact that you're forcing something flat to become doubly curved, and that was all due to Carl Friedrich Gauss's remarkable theorem. But the armadillo is a friend of Gauss because it has this semi-cylindrical sort of midriff. It's got this armored body, and this midriff allows it to be articulated into a ball. So it goes from being simply curved in the middle to something which is doubly curved, so it must respect Gauss's theorem as well. This is a schematic of what happens. It's got more or less a sort of fixed front and rear, and this flexible middle. And it does this because, and I haven't got a video of this, but it does it in the same way that a salamander might do this. It rolls itself up into a sort of tire, a ball to escape predators quickly. And so how does the armadillo do this? Well, the sort of central portion comprises these pleats, these ridges for sort of armor protection, but the pleats can open and close. And even in this simple rendition here, where I force the center of the pleats to lengthen and to shorten at the edges. You can see already the impression of a spherical surface on the right side emerging. If you take a single pleat and imagine it in its cylindrical configuration sitting between two parallel planes, and then you rotate those planes to create the sort of spherical journey, then moving from the opening in the middle to the outside, closing, you get the material. The material has to stretch. There has to be some compliance of the material to match that articulation, which kind of lends this then to a sort of family of structures that we call compliant shell mechanisms. And so you can propose some simple demonstrations of this. You can compare then against simulations, and you can simulate then the folding of an armadillo if you so wish. This is important, this relationship between double curving and the material stretching, because if you don't take account of that during engineering design, then things like your sort of tubular sort of Hoover hose becoming doubly curved will experience stretching that might be unwanted by the material and thus lead it to sort of failing prematurely. You also see this principle in things like bendy straws. Okay, so next half. So this is the mechanics bit. Thank you. This is a Shakespearean metaphor that's become clear in due course. It's all about jumping shape. This is a concrete column being compressed on the floor of the lab axially by this force, so it's under compression, and it's there to simulate the increasing weight of a building where it mounted vertically in practice. And you can see it fails, it bulges sideways. This is buckling, if you like. And Euler identified the simplest form of buckling, which is to compress a rod, and at a particular point that compression changes, it jumps shape to this lateral sort of bending, if you like. That allows the action of the forces applied to continue, but under energetically more favorable conditions. It's basically, there's less energy stored in that sort of bent shape rather than the compressed shape. Euler solved this problem as part of the sort of general suite of behavior of the bent wire, what is known as the elastica, and this was the first true solution of the application of his calculus of variation. So I think we need to frame this equation and put it out there, given what calculus of variation set by way of the analytical revolution that it was. Buckling, by definition, expedites shape change, so we think of it usefully for helping us. And I've got an example here of of a hoop, not a very circular hoop that you can see. There's a clasp at the top here where my hand is to keep the loop open. If I remove that clasp, it collapses into three sort of smaller loops that you can see there. Here, the buckling interchange or transition is not between curving and compression, but rather between curving and twisting. Because if you look at that little sort of curved strip there and the difference in the length of the red and green lines, if you twist something which is already curved, you gently uncurve it whilst adding some twisting to that. So there's an interplay there, and if twisting wins, then it follows that path. So I'm going to sort of shake this, and you see it's quite impervious to any sort of movement. I'm doing this all in plane, but if I twist my hand, then after a point, it jumps into sort of three loops, and that's very, very nice indeed. I'm working with the great Basile Oderly in Paris. We took it a step further, where if I sort of formalize what I've done there, I'm twisting this in a sort of singly directed sort of fluid movement. I can create the same sort of thing. But if I introduce some variation into that twisting movement, which is to say I kind of turn my hands one way or go the other way, I allow that to sort of take place, then I can create sort of 5 loops, okay? And if you know what you're doing, you can make 7, okay? But it's not very stable. Well, it might sort of jump up and give us something to laugh about in a moment. But anyway, Dominic Vella's group at Oxford looks at buckling in a slightly different way. They talk about this problem, the birth of a ruck in a rug, which is to say you have an Euler beam lying on a surface, and instead of the whole thing buckling sideways, you get this localized hump in the middle. This is what they call the ruck. And you see a ruck also forming when this ring of cells, the epithelium, spontaneously folds. The epithelium folds inside to create this internal structure that repeats along the length of the developing embryo to set the body plan for things like the digestive system and so on in a process known as gastrulation. It's a buckling process because what's happening is that the ring of cells wants to be larger. They're proliferating, they're getting much bigger, but it's contained within the shell. So the way in which that length change or that length increase can be accommodated is by the red inverting locally. And the arc length of the red is greater than the sort of the arc length of the blue shell here by the indicated percentage. And this was an attempt to frame the degree of deformation, or the degree of progress, if you like, in this folding embryo above by some people in the paper I'll show in a minute. So this is the formation of a ruck through buckling. We call it ruckling. It's happening within a cylinder, within a circle, within a ring, so we call it cylindrical ruckling. And it's important to note that that ruck just doesn't grow from nothing. It appears at a finite angle here, when we call that angle 2 theta min. And the corresponding growth strain at which that takes place, you can imagine to be the excess angle above 360 if you were to cut that ring and it was just to grow and overlap instead. So I looked at this problem and see this as a sort of mechanics problem that we can solve with the techniques that we teach our first-year engineering students. So we don't use calculus of variations. We solve for the equilibrium of that. We think about how that sits within the shell in terms of the geometry. And when you solve for the instance of buckling, ruckling, you get two formulas that are largely constants, except for this K term. This K measures the thickness of the ring to the radius of the ring that's deforming. And you'll see those, they differ in terms of the power to which they are raised. And this is important because developmental biology groups around the world attempt to sort of calculate these angles. They sort of measure it from experiments. They measure the height at the moment of inception of the ruck itself. And they kind of, and the reason for doing that is so you can find the level of growth strain that's taken place there as well. And so they plot lots of different sort of results from different experiments. They do simulations using software. And the red line that you see there is a calculus of variations model that contains a Lagrangian multiplier to account for the shell-containing constraint. It uses a hyperelastic biological material with large strains and large displacements enabled. And it's got a bifurcation algorithm to sort of capture the buckling instance. So that's all very well and nice. If you plot my results, you get that. You follow that red line almost perfectly. So we have a sort of mechanically transparent way of doing things. And the reason it works is because the process is remarkably simple, because that's kind of what biology does. It finds the simplest way to do things. William Shakespeare, 110 years before Euler was born, wrote, "And as the rat whose fever weakened joints like strengthless hinges buckle under life," a sort of metaphor for the midlife man, perhaps. But William Shakespeare was not a civil engineer. But you can see the sort of proliferation of sort of technical terms here that we now use within the sort of vernacular for describing our subject. Hinges, strength less, buckle, and joints and things like that. I think that's all rather lovely to assert that kind of cultural relevance. Buckling is derived from the French boucler, which means to bulge, which is derived from the Latin for cheek, where we get terms like buccal fat from. But I think, if our cheeks are bulging, we shouldn't be lamenting the failure of our structures through buckling. We should be celebrating them and smiling, not celebrating the failure, I'm celebrating the fact that buckling sort of features right at the heart of life itself. Okay, so the next principle is non-linearity, going beyond shallow. What I have here is a thought experiment. I've got two rods that are connected to each other by pin joints. They start off being length L each. They sit a little rise above the horizontal H, and the center point is pushed vertically, so they compress. So the S is shorter than the L, and you can write a little bit of Pythagoras. You can truncate that series using the binomial theorem. You can calculate the strain, and you find that that strain varies as H over L to the power of 2. It is not linearly appointed, but non-linearly appointed. If you set the limit of strain, say, equal to what you see in engineering materials, around 0.2%, then the sort of allowable H relative to L that permits that to take place so that you don't exceed the strain is about 6.3%. And compared to the linear result, that's a 30-fold increase. So this is what we call an example of geometrical non-linearity. You're creating a large movement, but you're not creating excessive straining at the same time. And furthermore, if you push that arrangement inside out, because the bars naturally grow in length again, they relieve themselves of that compressive strain. You create something that can be inverted. You get this second shape, and you get a very large movement at the heart of it. And this is a little sort of demo to illustrate that. I'm pointing at some springs on the left and right side. Oh, it does work, the sound. Yeah. And you saw that, you see the center moves through quite a bit of distance, but again, look at the sort of movement in the springs. The springs are hardly sort of compressing to signify that there's very little material strain going on there relative to the movement of the center. And it's invertible. It's happy to lie there. Here is, that might be a bit loud, here is the continuous incarnation of this, which is half a tennis ball, and you can turn half a tennis ball inside out. You can invert it as well, and it's happy to be in that configuration. Plop. And it won't revert. And that, to me, is an interesting sort of problem to try and solve from a mechanics perspective. But we're reminded that Gauss tells us that if you start off with something which is flat that becomes doubly curved, you might expect there to be some in-plane straining and some out-plane curving taking place. And if you'll permit me to be a little bit mathsy for a couple of slides, I'm going to apportion two functions, phi and w, to describe that variation as functions of the coordinates x and y within the surface. And what Gauss tells you to solve is this particular fourth-order partial differential equation. If you go inside then the surface and look at what the forces and moments and in-plane torques, basically all of the mechanical stuff inside, if you look at the rates of change about what's happening, and then kind of sum that up and sort of bring everything into resolution, you find that you get this deformed equilibrium equation, a different equation, which also has to be solved. So you've got to solve these two sort of fourth-order nonlinear partial differential equations together in order to sort of describe problems like the tennis ball turning inside out, and you can. So we imagine we start off with a spherical cap. It has some radius of curving r, 0. You turn it upside down or you invert it, you push it through, it acquires a new radius of curving r. Kappa is the term, the Greek term that we often use to denote curvature, which is the reciprocal of the radius of curving, so a high curvature means a low radius and vice versa. You allow the width of the cap to vary and the thickness to vary, and you find that this inequality emerges that describes the feasibility of this inverted shape. And really what that is just telling you that you need a sufficiently wide cap for this thing to be invertible. And I've got a little demo to show you here. I've got a pair of butchered tennis ball parts. You can sort of see here, there they are. And the one on the left or right is insufficiently, I can't make that stay inverted no hard I try. This is a little bit wider, it sort of supersedes the threshold, and it's quite happy to be inverted, and it can revert as well. So that kind of shows that these things, that this sort of method has some kind of credibility. So you've got an initial shape that has no loads applied. You have a second shape that's invertible. It, however, is not stress-free in the case of the tennis ball because it starts off as a doubly curved shape and then becomes another doubly curved shape. So you don't mitigate the stress. Some of it remains, but nevertheless, you create a state of internal equilibrium with itself, even though no loads have to be applied. And the existence of these two states means that you have a bistable structure. So what you do then is you amplify the level of parameterization. You allow these caps to be curved differently in two directions. You might add a little bit of twist, and you might use materials that are not isotropic, but they have properties that differ in sort of orthogonal directions. And you plot the degree of stability as a function of the initial shape. So you create these regimes, these sort of landscapes where every point is a starting configuration. And the gray, the light gray, tells you where to expect bistable behavior. The white is monostable, and so the boundary between the gray and the white is a bit like the threshold that we saw before. But the difference between these is in the Poisson ratio, if you know what that means. And the landscape in the right there has these extra sort of darkened regions which indicate three stable configurations. You have tri-stable behavior. And this was discovered by my good colleagues in the continent, Stefano Vidoli and Corrado Marini, who really took this to task and sort of amplified, widened those regions of feasibility by working with particular material parameters that we don't need to go in here, but showing that these things were absolutely possible. So if you want to create sort of simply shaped cells, or shells that have sort of a relatively simple shape, then they are multi-stable if you work with materials that are orthotropic, they're not isotropic, that have a high torsional stiffness. This is what also came out of that study of theirs, and they have a high Poisson ratio. And this sort of segues nicely into the role that constitutive material behavior has upon multi-stability. And you've all heard of carbon fiber, glass fiber, reinforced plastics. These are what we call laminated composites. Essentially, you have layers or laminates with fibers running through them that give you strength in two directions, different levels if you like, sat within a matrix, so again a different material, and by varying the relative orientation of fibers, the number of layers and so forth, you can begin to tailor the sort of material that you need to create something like this bistable tube. So it's a cylindrical tube, as you can see. It's got this bistable configuration, but I think I should let my colleague Simon Guest demonstrate the bistability. Rather, let's see that again. So this is a bistable tube, and Simon runs the lab with me where we make these sorts of things. Don't tell health and safety. Anyway, so you don't need access to fancy composites. You can work with this structural architecture, which is a grid shell, and the grid shell is simply that. It's a surface that looks like a grid. You've removed material. In removing the material, you lower the sort of bending compliance. You make it more flexible in bending, but you keep the torsional stiffness, so you're elevating the torsional stiffness in comparison. And Evros Lucchese, my former PhD student now at Bath, was the expert in making these, and you can clearly see them being bistable. They can move between these two configurations quite nicely. And Evros was also the first to produce a tri-stable glass fiber reinforced shell here. You can almost see through it. It's so thin, and you can see the direction of the fibers, but this is three clear load-free shapes sort of in evidence here, and as I said, he was the first to demonstrate this in practical terms. Okay, so the next principle is activation, which has the tagline inelasticity, residual strains, and I'll explain what we mean by that in due course. What you're seeing in the picture here is a rubber cap with a magnet coming from the right, which is exerting an effect, a force on the cap remotely to cause it to invert, and the reason for that is because the cap has got magnetic particles in the rubber. So this is an example of a non-mechanical stimulus having an effect on the material. The more familiar example of this is where you take a metal and you heat it, and two different metals heated by the same amount will expand by different amounts, but if you connect them together, they will curve to accommodate that differential expansion, and that is known as the bimetallic strip. The bimetal strip, because it's conductive, often features in electrical heating circuits where the electricity itself has been used to heat something, but that heat gets diverted onto the strip at a particular point in order to cause it to curve upwards, break the contact, and stop the heating. And this is the principle that stops your kettle from boiling dry. But another little example here, a sort of frivolous example, is of, maybe I should just put that back up again for a minute. What I have here is a little cap, and you can hear it sort of click through. It's a bit like that sort of smaller tennis ball cap. It's got a single configuration. It doesn't want to be bistable. But as this sort of picture shows here, if I rub it with my thumb, I'm kind of creating an activation curvature that puts it in the direction of that, that second shape. And then there we go. You can see as the heat bleeds from that, and I've got another one here that's there we go. I need to get my thumbs going. Here we go. And that other one will go shortly. Who's taking bets? There we go. Nice. So the heat bleeds from that. It releases that second configuration. That's a dynamic snap back, and that manifests at the particular jump that you saw there. Now, I was interested in getting a little bit more out of bimetal because it is a quite small strain. So how do you maximize or magnify that? So what you do is you coil your strip into a helix. So you get a lot of length in a small volume. And this is what it looks like to start with before you heat it. And when you heat it, then that curving sort of multiplies through, and you get this relative rotation between the ends. And furthermore, if you take that coil and you wrap it into a sort of a second coil to create what's called a coiled coil, then that relative rotation in the first case between the ends now manifests as a twist on the local direction of the bigger coil, which sort of leverages the sort of axial movement, if you like. And so you get this kind of hierarchical amplification. Don't worry too much about the maths here, but the point is that in this formula here, the sort of strain that we see from the movement of the actual coil relative to the bimetal strain, which is this lambda term, you get several hundredfold amplification taking place here. And the best way to demonstrate this is, of course, with some experiments here. So along the top, we have 3 coils. Along the bottom, we have 3 ordinary coils. The top left is dragging the electrical cable with it that is used to heat it. The 3 that are glowing orange, that's from security lamps that are heating it, that you can see there. And on the far right, the 2 top and bottom are, in fact, piezoelectric coils. And I became interested in this project because I did some work for a really good man here in Cambridge, Tony Hooley, who proposed these kind of coils as a way of driving motion in all sorts of electromechanical devices. And the University of Birmingham solved the problem of how to make them out of ceramic, because piezoelectric is a ceramic, and they are electrically driven. But don't look too carefully at the one at the top right, because I managed to break it during this experiment. What do you see? There it goes. Okay, so sorry about that. So if you, well, we don't have access to piezoelectric and bimetal, you can generate the same sort of effect using tracing paper. Tracing paper, when it sits on top of water, it swells, it generates a differential expansion, and that therefore results in some kind of curving. So I'm going to sort of try and illustrate this using a plate just as background and some water, just so that you're convinced it's not a special water. There we are. So there we go, some water on the surface there. Now, tracing paper, I should add, of this particular type here, has, where the arrow is indicated, a preference for swelling. It will swell in that direction along the length of the paper. So that's where the rolling will take place. And I have some prearranged strips that I've cut here. And if I put these on the surface, I'll put one on to start with, you'll see, you can just about see it here, you'll see after a time it starts to curl along its length. So it's doing what it should be doing. If you have some strips that are cut at right angles to the paper, like this one, then you should expect to see it roll across. And it does. And then finally, if you have some strips that are cut at an angle to the length, then it will helically coil, as you can see here, and do something rather lovely. Let's put a few on there for the sake of theatrical performance. There we go. And yes, so this is the exact same effect. There they go, coiling away. So that's that. So the technical bit of this, the inelasticity bit, means that when you're looking at the stress-strain behavior of the material, you're able to stimulate an offset, a controllable offset. It gives you this parameter epsilon A along the bottom, about which you have this sort of linear mechanical response. The same is true when you work with plastic deformation in things like metals. If you yield a metal and then you offload it, you generate also this kind of epsilon A, about which you have some mechanical behavior. Evident linear behavior, that is, but you've only got one shot at that, because the processes behind producing this just give you one shot, because it's a forming process. But this allows you to do interesting things like make a flick bracelet, and I'm going to just move this out of the way. And a flick bracelet is, you might be familiar with this. Well, first of all, I've got just a piece of sort of tape measure here. And we all know that when you bend a tape measure, it sort of wants to be straight. I'm going to leave that there because we're going to come back to it in due course. And what I have here is a pre-prepared sort of piece of tape measure. Okay, so there it is here. If I take this tape measure and I kind of coil it around the top here and pull through, then I've imparted a sense of that sort of coiling permanently. It's sort of built the shape into it. But because it's a tape measure, because it has some sort of curving this way, a bit like the pizza, that gives it structural depth that prevents that shape from being realized until such times you kind of lose the structural depth. Off it goes into this bistable configuration. So what you have, as you say, is this sort of thing called kids call it a flick bracelet. There we go. It sort of wraps around, and that's very nice indeed. So what you're doing there is using the consequence of this plastic forming to create a sense of a bistable shape that you then access through changes in geometry of the structure, so the flattening of the flick bracelet, if you like. And if you take several flick bracelets and imagine orienting them up and down and repeating that pre-stressing process, you get something that looks a bit more like a sheet, a kind of gently corrugated sheet, rather than a sort of wide tape measure. So something that looks a bit like this. I'm not sure you can see the corrugations particularly well. There we go. But this has been pre-stressed in such a way that it too will also roll up into this tube that you can see here. This is also bistable. I knew this bit was going to involve a little bit of running around. And so that's quite nice, that's quite lovely. And again, it shows the concept sort of being extended to different structural forms that you report on. And this is just what you saw there. It's sort of rolling up. Apologies for the poor lighting there. And then the final demonstration of this is to do with the Venus flytrap and the operation of that. I'm not going to show the death of a fly on screen. It is the BBC One after all. It's probably going to be reported with impartiality and a lack of political bias. But anyway, oh no, let's get past that. I do have a model of the flytrap. And here we go again. So here is my Venus flytrap, as you can see here. And I do have a fly specimen here. So the fly, you can see there, that's the fly. So the fly lands in the Venus flytrap. It triggers the movement of a hair. The second time it triggers it is when the flytrap activates. It doesn't do it the first time because that could be a false alarm. And there it goes, and the little fly is clearly toast. Anyway, running to the heart of that is, of course, a flick bracelet. So here you can see it there. It's kind of got this sort of tape-like constituency. In the Venus flytrap, that kind of open configuration is this equivalent to the straightened configuration of the tape. It's held open by turgor pressure, so the fluid inside. And when it senses the presence of the fly, it evacuates some of that fluid. So in the same way that me pushing down on the top of that creates that sort of reduction, if you like, in the structural depth, so the removal of turgor pressure from underneath does the same. And so eventually it does something like that, and it traps the fly, as you can see. So this was an interesting problem. I did not solve this. This was solved by other people elsewhere, but this idea that plants could move very fast without muscle is borne out by this interaction between sort of materials being pre-stressed, pre-strained, and having this sort of bistable capability. Okay, so we're near the end now. We're getting close to the end. Localization, stable propagation of the unstable. If you take a tape measure out of its housing and let go, there's this chaotic dynamic explosion. It wants to be straight, and you see this wonderful sort of interchange between elastic potential energy and kinetic energy. And Sergio Pellegrino, at the first day of my PhD, said we need, well, didn't say these words exactly, but said that we need to tame this motion, because it's that motion that is used to drive the deployment of these sort of forms that I showed earlier in a controllable, reliable way. So if you just have little bits of bendy metal driving this and you don't have motors and cables, then it's cheap, it's lightweight, but you run the risk of it not working. So we've got to tame this motion. And to tame that motion, you have to understand the sort of structural mechanics of a tape measure before thinking about its dynamics. And we call them tape springs, but we really mean tape measure. And so, and you probably know this. Here we go again. If you take a length of tape measure and you bend it, it forms, it sort of snaps through, and you get this kind of unstable behavior. But if I turn that to the side, you'll see it forms this hinge. And that hinge has a remarkable property of having a radius of curving which is constant. And the torque that I'm applying here to sort of maintain that is actually a constant as well. So you have the unstable feature at the start creating something that ends up having these sort of stable properties, hence the sort of tagline that we talked about. And so this is just some simulations in the bottom that confirm that, but really, to reiterate, it has a constant radius of curving, so as you articulate it envelops more subtended angle. And not only that, if you assume that the strip has a constant, has this sort of circular arc cross-section, in a wonderful calculation from 1954, Vush showed that the radius of curving of that hinge was exactly the same, that R equals R. And to sort of explain why this perhaps might do what it does, we go back to a lecture by Maxwell in 1875 to the British Chemical Society on the elusive van der Waals equation, and forgive me if I get the sort of description of this wrong, but the van der Waals pressure-volume equation describes the transition between a liquid to gaseous state at constant temperature. So you have this kind of oscillation, this sort of propagation of liquid into a gas and vice versa, depending on whether or not you're heating or cooling the system. And it's elusive because you don't really see that in theory, but what you see in practice is that interchange taking place at constant pressure, P star, a sort of propagation pressure where the states sort of move in and out of each other. And Maxwell said, well, if you can find a line that you can draw horizontally to give you 3 intersection points where the area above and below are equal, that is your constant pressure. And so we thought, well, could we deploy this explanation, the Maxwell construction, as it is known, for describing what's going on with our tape measure? Why does it form this particular sort of hinge behaving as it does? And you can imagine the hinge a bit like the gaseous state, highly agitated, very curved, and the straight bit's a bit like the liquid. So you have your two-phase description. So you need then to describe the bending of this. So you need a theoretical description of that. We take a strip, we bend it by sort of moments, these torques at either end. You figure out what the curvature is. The curvature kappa bar on the right is measured against the radius of curving to start with. These are not insurmountable problems. You can solve for the moment curvature response, and you get something which is highly nonlinear. Looks a bit like this. You can draw a straight line across, 3 points, first and third, describe the original straight state, slightly curved, but very imperceptibly so. And then the hinge, the more highly curved bit, setting it equals area, setting the areas above and below equal. You then get this curvature here, kappa bar star, almost equal to 1, but not quite, because Wüst assumed that the thickness of the material was very, very small indeed. If you allow for some ordinary sort of thicknesses, some realistic thicknesses, and you change the angle that is swept by the cross-section, then you get these sort of traces from that construction that begin to approach unity, but not quite, but nevertheless give some kind of credibility to this method as a viable way of explaining what's going on with these hinges. And what you can do even more so, interesting, is you can amplify once more the parameterization associated with this. That is to say, if you have a tape measure like this where every cross-section is the same, the elastic domain is thus the same as constant. But if you allow it to have some variation, that is to say, you can see the width changing here, then the elastic properties are changing. That is what I mean by the elastic domain varying. And the sort of short outcome of this with regard to the Maxwell construction is that, yes, you get the second phase forming, but the properties of that phase will depend on the level of deformation that you impart to this. So if I bend this, and let's try and get this right, and thanks to Jamie Clarkson, the sort of PhD student who sort of worked in this and sort of figured it out, you'll see it sort of forms a fold here. I'm just trying to get the orientation right. But as I increase the rotation, you'll see it jump into a second phase that has a different set of properties. And you could go back and repeat, and it does it again, jump, and there it goes. So again, a vindication of the sort of credibility of this method in terms of its application in a mechanical context. So that's the taper it's bringing. Now the last and final section, confinement, if I have time, 2 minutes. Is that all right? Hierarchical buckling. Right, I need to go back again. So I've got here a little foil cone. So I make this by just taking some mylar, cutting a wedge out of it, putting some sellotape on there, creating a little cone, and now what I'm going to do is force it into a position it doesn't want to be in. I'm going to squash it, and I get this lovely sort of fingerprint formation taking place there. If you change the operation, if you instead of working with a little cone, you work with, again, a cylinder. So I've got this kind of foil cylinder here in the end, and if I squeeze it, you can see it sort of buckles, and it's quite messy. But if I put this tube up the center, so that I introduce a constraint that prevents that from sort of buckling. It forces it to spread in line with what I said, the sort of hierarchical buckling pattern's been triggered. You'll see it sort of then go into this lovely sort of dimpled pattern here, which is quite nice. If I very quickly go to... Now, you may be familiar with the fact that the golf ball is dimpled because for the size it is and for the speed it's driven at aerodynamically, that's better being dimpled than being smooth. So we stuck our cylinder in a wind tunnel in the engineering department in a smooth configuration, and then we brought the end plates together and we measured then the drag force between the smooth and the dimpled configuration. So plotted vertically here, we have that drag force. Running to the side, we have the speed, and the dimpled configuration has a much lower drag coefficient. So you can imagine perhaps your car or vehicle having this sort of surface that you could switch on and off to lower the drag force to achieve better fuel economy. Of course, I'm not an aerospace engineer as such. I'm not an aerodynamics person, aeronautics person, but this sort of thing could be quite fun. We've got to be careful that we don't repeat what we do. Nicholas Hoff did an experiment in 1966. He created these very thin metallic spheres that were impressed onto these solid cores. There was a bit of an air gap, I should say, between them, and he then evacuated the air, forcing the contraction of the sphere onto the solid core, a bit like you saw with the cylinder, and produced this dimple pattern that you see. If you imagine, instead of working with solid objects, but things that are elastic, with an elastic film, and the two things grow together, but the film grows much more quickly, it's kind of confined, it becomes contracted onto the surface. And imagine that you can work with rugby ball shapes instead of spheres. Then you get this in simulation, and this is not my work, this is Chen and Yin from 15 years ago, but you get this whole morphology associated with fruit and veg, if you like, which is quite impressive. The thing about this, a lot of this is numerically sort of driven. It's all done by simulation. So we wanted to try, and this is the last thing to show you, to try and make this work in practice. What I've got here is so this is just polymer that you cast, and then it settles as this sort of rubber sort of shape. And on this side here, I've got some other polymer that you spray onto this, and it sort of cures as well, and you've got that configuration. If you imagine casting the white, then stretching it, and this is why the holes are there, and then spraying onto that the red. So the red is then sprayed onto that, not knowing that the underneath is stretched, and you let that cure, and then you let it contract. So what happens is that the red is now contracted, but it has this interaction with the underlying sort of white. You get something that looks like this. You get a brain, okay? You get something that looks like a brain. You basically can show that these things have, that these sort of principles run to the heart of the kind of evolution of, structure in biology and so on. Okay, so keep your topic relevant. We live, as I say, in an age of fast-moving stuff. It's up to us to keep our subjects alive. Write a textbook. Remember, early books are brilliant because they didn't have computers helping them to solve very hard problems. Amplify parameterization. This is what we do all the time. We find compact models of simple demonstrators and then allow that to push us in the direction of things that are interesting. And remember, it's all about scholarly endeavor, and I wouldn't have been able to do half the stuff I have done without the brilliant sort of collaboration with these postgraduate scholars over the years. I should acknowledge Chris Calladine. He was responsible, along with Sergio Pellegrino 25 years ago, for getting the job that I have now, probably. Chris was the outgoing head of structures at the time. He saw structural engineering bigger than, structural mechanics bigger than structural engineering, literally wrote a book on it, and he sadly died a couple of months ago. And finally, to Mum and Dad, I was their firstborn kid. They were young parents, working class, Northern Ireland, time of the Troubles. I had more ginger hair than everybody in the village, and yet they fostered my sort of academic leanings without any sort of judgment, despite themselves, having to leave school early and go out to work and so on. They're still with us, by the way. And so I should sort of acknowledge them properly for that. And thank you for listening. Sorry I've overran. I'm very happy to take questions.